those who are willing to do the exercise with us, I'll try to do it slowly. And because you can see my window here, you should be able to follow and do it with me. We don't use pre-written code, but we'll do it all in front of you. So our idea in doing a spirograph, of course, we don't want to put it all into our control window, but we want to have it all in a file. So I open a new file and I make a comment that this will be our spirograph. What do we need to create a spirograph? We need to have a couple of points that we turn into a function which we will then display with x and y coordinates. So let me start by defining an array of points. If you remember, an array of points can be defined by giving the start and the finish point of that array. For example, if we use sine and cosine, a multiple of pi is always something that's advisable. So let me do, for example, multiples of pi, say 20 times pi. So my array will be from 0 to 20 times pi. However, because as I have written it, if you remember, this will only be integer step size. So if you want to have a step size that is smaller than an integer, for example, 0.02, you have to put that in the middle within colons. And this would be a way of setting up our array. If I just execute the code as it is, I can see in my command window that I have created 3,142 data points between 0 and 20 pi. So that will be something to easily help us make a nice spirograph plot. For the print, I'm just setting up a figure, maybe call it figure 1, and I start with the command hold on. Why is that? Because we want to successively create our points and put them on the figure one after the other. And in order not to lose the previous points, to preserve all the previous points, we have hold on. That means keep all the previous plotting points in the figure. Don't erase them when you plot a new one. If you want to undo it, you have to put hold off, but for now, we need hold on. And for those who have done it, it's clear, but what we will do, we will have to define a for loop. A for loop is defined with typing for and is ended by putting in the 3 letters for end. So how do we define a for loop? We need to say how many times is this loop going to run. So if we call our index for the for loop k, then k needs to run from the first point to the last point. What is the last point? Well, we don't need to calculate it and we don't need to remember. We just let MATLAB figure that out. That's the length of the array points. Length means it will give you the number of points that are stored in this array. If you just execute length by itself, you can see in the command window there's 3,142 points. And this number is what we will need here as an information because it's the last thing to be processed within that loop. Then we make things a little bit easier for us by putting the current point into a value called t. And this is now going to be our for loop index, which is k. So for every run in the for loop, we assign the current point to a value called t. And then from this t, we can start to calculate our function. So we get our x coordinate. Typically, we have some combination of sine and cosine. I just invent something arbitrary here. The sine of t minus 5 times the cosine of t. And you know that the spirograph images always get nicer when these frequencies are not exactly the same. But we have some multiplicative factor here. So I just arbitrarily use something which is 1.9. So we have some combination of sine and cosine for the x-axis, and we want to have something similar for the y-axis. Let me do that quickly by just copying it. What could we do? Maybe I exchange, I make a positive cosine here, and I choose another frequency here. And of course, this is now completely arbitrary, but say a larger number, which is a higher frequency. And if they are incommensurate, you know that they will give these nice toroidal shaped figures, which we can then display. And for each time such a function value is created by this assignment to x and y, we can, of course, start to plot it. What do we need to plot? Well, we need to plot x and y. To have it a little bit nicer, you know, by default, MATLAB will then combine them with lines. If we don't want to have that, we can give another argument. Within quotes, we can define the color with which we want to plot. So, for instance, red. But we can also define a type of marker, say points or maybe small circles. And this is a way of saying that make red circles for each of the time points and don't connect them by lines. And that should be it. This is all that we need for a for loop. And if it runs well, let's see how we do it. I make a clear command window in the beginning so that we will see any error message displayed in the command window only and nothing previous. So this created now our spirograph image. And if I make this image slightly larger, you can see that this is a fairly nice image. We have some funny shape, and that's of course up to you to modify and plot and experiment with it to get a nice graph. The one thing that I want to add today as a sort of a tip to keep experimenting and digging deeper into MATLAB is that, of course, there's nothing that prevents you from making things more complicated. And one way to make it more complicated is to use the same thing as before and have it assigned to a new variable, which is now called z. So so far we had two variables, now we have a third variable. And if we do this, not really clear, give some other value, say 35 here, make a new function, which is called z, which is yet different from the previous ones. We would, of course, like to see all three plotted together, namely something like x, y, z. This will give us an error because plot is not made for this. However, MATLAB has a functionality that can deal with three coordinates, and that is a function called plot3. So if you look at this highlighted in yellow now, if you use plot3, you need to provide three arguments to display, and we can see we have them as x, y, and z, which will give you an image if you run this code, which looks very similar to the previous one, but the reason for this is that it's displaying only a two-dimensional projection. So if I make this image larger, in your graphics toolbox, in the toolbar, you have, among other things, a zoom, rotate functionality. If you select this, you can then start to rotate this whole image around. And you can see that it's actually quite a messy thing that results from this thing if we produce a three-dimensional graphics. And if you experiment with this, if you make points a little bit denser, you can make a nice toroidal shape with a hole in the middle and use this for your convenience. Right, final thing, if you don't like the plot background, if you want to make a bit of a plot that is even more fancy, I just go back to our previous two-dimensional plot as we had it before, and there is a functionality if you have such a plot as we have it here. What you can do to change the background of the plot. So the actual canvas where the points are plotted, there is a function which is a bit complicated, so I'm just going to show this for you. You use the set function on GCA. This is the get current axis command. And you can choose within quotes the American way of writing color. And color expects you to give it 3 numbers by which you can choose what color the background will look like. So I'm going to show you 0, 0, 0, which is all is black, so there's no color at all. So if we get our plot back, make it big, and then execute the plot background, you can see that it's now black background, and it's a way of making your image a little bit cooler if you like to do so. To understand this command with the 3 figures, it's called the RGB code, standing for red, green, and blue. So RGB red, green, and blue means if you have it set to 1, 0, 0, it will be all red, which means you don't see the points because the points are red and the background is black, the background is red. But if you take the blue, for example, you will have the points in red and the background in blue. So there's something for you to experiment with. Numbers have to be within 0 and 1. Any combination you can choose, and you can try to find your way into coloring in your plot as you like. Okay, I don't need to save this file. This concludes our first exercise, and we are ready to go into matrices. And I will hand over to Rob for this second part.